Assessment of residual effectiveness for water-repellent treatments for stone buildings. Water absorption test on the monumental complex Cathedral of San Zeno and Baptistery of San Giovanni in Corte in Pistoia. Authors Martelli, Teresa Salvatici, Carlo Alberto Garzonio, Maurizio De Vita. Good morning, my name is Martelli, and what I'd like to present to you today is the result of my doctoral research conducted from 2016 to 2018 on outstanding and very well-known Italian monuments. This presentation synthetically retraces a specific activity conducted over the two historical buildings, which also represents a peculiar methodological path aimed at documenting the results of systematic investigation conducted at a distance of time after the application of specific substances for specialist restoration. I'll briefly show you the table of contents of this presentation. First, I'll explain the scope of the research. Then I'll focus on the method and the challenge of the chosen method. Then I'll illustrate you the performed test in details. And finally, we'll discuss the results of the study. When talking about monuments, we all agree in recognizing the importance of preventive and temporary planning of conservation, but we should also admit that its practical application is rather difficult to perform, mostly due to the lack of data regarding the durability of treatments. This issue is influencing the management of preventive conservation of cultural heritage, and unfortunately we must note that the choices of conservative intervention are often made after the degradation phenomena have already started. The investigation into the residual effectiveness of conservative treatments of degraded architectural surfaces appeared appropriate to address this theme. The study we are going to present focused on the possibility of measuring and quantifying the residual efficiency of protective treatments used in conservation of stone monuments after a certain time from their application, and therefore evaluate their durability. But the big challenge of this research has been to perform this assessment exclusively by means of in situ tests and in real condition, thus tackling some issues that pertain to the architectural scale. So it should be emphasized that this research necessarily brings with itself some approximation inherent in being an ex post survey, in which not all factors could be kept under control from the beginning, but for which it was possible to make hypotheses. For example, the quantities of product absorbed in the various points are not known, nor how the products were applied. Consequently, the research dives into reality and contingency, reading the actual yield of the treatments on the stone examined, and not the theoretical one obtained in laboratory tests under controlled conditions. Furthermore, and this is something I ask you to keep in mind, a simple test as the contact sponge water absorption test has been stressed and rather used as a comparison test between treatments with different and known aging than as a treated-untreated test. To meet these needs, some monuments that had undergone conservative intervention in recent years needed to be chosen. The Cathedral of San Zeno, its bell tower, and the Baptistery of San Giovanni in Corte in Pistoia suited the aim for several reasons. The same lithotypes, the same environmental conditions, the different states of preservation, the fair number of documented restorations performed at different times. As we said, on-site tests were carried out on three different lithological types: white marble, serpentine, and grey sandstone. For each type of stone, significant slabs with known treatment and year of execution have been chosen. Each point was marked with a 2-letter and 2-digit progressive number code. The choice of the test point was made through a combined evaluation of past restoration information and of accessibility. The following restoration works were taken into consideration: on the cathedral, no intervention, date 0, and a 1999-2000 intervention. On the bell tower, a 1997-2000 intervention. On the Baptistery, an overall restoration carried out between 1999 and 2000, and several new interventions in subsequent years, 2014, 2017, 2018, on the various fronts of the Baptistery, as highlighted in the figure. We detected that white marbles, mainly ebon marbles, but also some travertine, were all treated with siloxanes. We also detected some shalby on many travertines of the bell tower and on some slabs of the Baptistery. Serpentines were all treated with fluorinated elastomers. Grey sandstones were treated sometimes with ethyl silicas, sometimes with fluorinated elastomers, and sometimes with siloxanes. You can see the framework of treatments of the different lithotypes on this table, where you can find for each slab or group of slabs the year of treatment and the identified product applied. What did we do after? As we said earlier, the contact sponge water absorption test has been used as a comparison test between these treatments with different unknown aging. Tests were carried out on several slabs for each lithotype and treatment, and by a single operator, to avoid introducing any error due to different manual skills. The amount of the absorbed water was, as usual, calculated according to the known equation. The tests were all performed in just 2 days in similar climatic conditions in temperature and relative humidity. A specific sponge has been used for each lithological type, and during the test the environmental data were also detected: ambient temperature, relative humidity, and slabs contact temperature and humidity. Where possible, the extension of the sponge fingerprint on the stone and the time for drying was also detected. Some tests were performed as a validation of the whole test system in order to estimate the influence of stone's superficial grain size or the influence of the presence of shalvi, that is, white flesh with lime milk. For now, in the table you can see an example of the performed measures per point. The short time here at disposal does not allow us to dwell on the details of the measurement, which, however, you will find entirely reported in my doctoral thesis, reported at the end of the article, and freely available consultation. Here I will report on the main results. Water absorption tests returned data ranging from 0.44 to 5.98 mg per square centimeter per minute on white marbles, from 0.744 to 4.938 mg per square centimeters per minute on serpentines, and from 0.69 and 11.565 mg per square centimeters per minute on grey sandstone, as shown in the graphs, where the amount of water absorbed in milligrams per square centimeters per minute are plotted on the y-axis, while corresponding test points, year of treatment, and exposure are plotted on the x-axis. What about white marbles? The water absorption data show discrete differences between the slabs with treatment carried out in the year 2000 and those with the most recent treatments, except in the case of point AM7, treatment year 2014, a slab of poor quality and which appears very degraded, used in fact as system validation. However, interesting results derive from the comparison between absorption of the AM 1, 2, 3, 6, and 8 points, all with treatments ascribable to the year 1999 to 2000, and the absorption values of the AM 14 point at 2014 treatment. The figure shows how the absorption detected in these elements are decidedly low compared to those of point AM14 with a polysiloxane treatment 2014, exception in the case of AM3, that is a travertine with large pores. For the serpentine, the distribution of the highest absorption peaks appears more tied to the state of conservation of the surfaces than to the age of the treatment. In any case, the decidedly lower absorption is still that of the last treatment carried out in 2017 with fluorinated elastomers used as anti-writing in the lower part of the side 3 and side 4 facades. Finally, grey sandstone is the lithological type that showed the greatest excursion between the treated and untreated absorption data, as you can see in the figure, with considerable differences between the slabs with the oldest treatment, years from 1999 to 2000, and those with most recent treatments. 2 slabs were also identified to assess how much the surface grain of the stone could affect the extent of capillary absorption, points AA5 and AA9, with the same year of treatment, on which to compare the results. Finally, also in grey sandstone, the comparison between the water absorption of the whitewashed parts is interesting, even if in this case less significantly than for marble, since no sandstone was found with bleaching outside. At the end, the assessment of the residual effectiveness of treatments have been carried out considering the data of points AM5 and 9, average for 2000 treatments, AM14, 2014 treatments, AM11, 2017 treatment, AM13, 2018 treatment for white marbles, AS1, 2, 3, 6, and 9, average 2000 treatment, AS5, 2014 treatment, AS7, 2017 treatment, AS8, 2018 treatment for serpentines, and AA1, 2, 3, 5, and 4 average for 2000 treatments, AA7 and 8 average 2014 treatment, and AA6 2017 treatment for grey sandstone. For all the lithotypes, it's possible to read out those slabs with older water-repellent treatments, about 20 years, give back significantly higher absorption values than the slabs with the most recent water-repellent treatments, 2014 or 2017 ones. The data relating to the areas treated in these 2 years also differ significantly from each other. The general overview of this dataset can be summarized in this figure. The absorption values of the 3 lithotypes are grouped by year of treatment, each with its own treatment. It can be noted how water absorption is strongly reduced by recent treatments on marble and sandstone, while a reduction is less appreciable on serpentines. Which was the next step, and this is the main point of the study. According to the literature, the effectiveness of water-repellent treatments applied 18 years apart can be assumed equal to 0. Thus, assuming treatment efficacy equal to 0 for the absorption values related to the treatment carried out in the years 1999 to 2000, we'll call it TF equal to 0 effectiveness of the treatment, and assuming treatment efficacy equal to 100% for new treatment with an estimated water absorption value of about 0.2 mg per square centimeter per minute, we'll call it time 0, T0, maximum effectiveness of the treatment. In analogy to the studies conducted by Ferreira and Delgado, using this relation, where AATX is the water absorption data for a treatment with a known agent, we can get these percentages of efficacy in reduction of capillary water absorption values. The tables show decreases in treatment efficacy in 4 years from 2014 treatment to 2017 treatments of 29.58 for white marble, 50.47 for serpentines, and 37.29 for grey sandstones. Now, let me briefly summarize the main results of the study. The method proved to be valid to evaluate the durability of different types of conservative treatments for stone, and these first tests have shown that siloxanes applied on marble and sandstone and fluorinated elastomers applied on serpentines have an immediate high water-repellent power 1 year after treatment, but a significantly lower degree of water repellency 4 years after treatments. As we have seen, minus 30% for white marbles, minus 50% for serpentines, and minus 38% for sandstones. This provides useful elements for the drafting of maintenance plans for monumental heritage. In fact, the found loss of effectiveness of the initial water repellency would mean that the stone should be retreated after 2 or 3 years in order to guarantee high water repellency and adequate protection from the effects of pollution. On the other hand, the protection of stone surfaces with lime milk whitewashes seemed more effective and stable over time compared to water-repellent treatments with synthetic polymers. These, at the moment, are the main results of the study. But here is the last important point I'd like to tell. The research could shortly provide further results. A monitoring slab, treated-untreated, for each of the 3 lithological types has been left for further comparison. Datasets that will derive will complete the forecasting framework with a time 0 of real maximum efficacy. This will enable having a more reliable estimate of the drop-off effectiveness over time. Water absorption could indeed be annually detected in the coming years to approximate a relatively reliable curve of decay for the specific conservation treatment studied. You would find an account of the new monitoring plan I'm talking about in the presentation Martelli-Bannett's thesis. Well, that concludes my presentation. Thanks for your attention, and please do not hesitate to contact us if you need any further information or would like to make any comments.